Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to go over what this coming section is about. In the last section, you learned about the architecture of a neural network and how to pass data from the input to the output to get a probabilistic prediction. We know the meaning of those outputs. It's the probability that the input belongs to each class. But our problem is that all of the weights in the neural network are random. So those output probabilities are also random. In other words, they aren't accurate. In this section, our focus is going to be on how to change those weights so that they are accurate. If you recall from logistic regression, the idea is your training data will consist of input and target pairs. Your goal is to make the predictions as close to the targets as possible. The way that we do this is we create a cost function. The cost is large when the predictions are not close to the targets, and this cost is small when the predictions are close to the targets. And so like any good businessman, our goal is to make our cost as small as possible. If you recall, the method we use to achieve this is called gradient descent. Gradient descent is a little harder with neural networks because the equations are more complex, but you'll see that as long as you're careful with each step, the derivations don't require any new skills. In this section, you'll learn that gradient descent has a special name, backpropagation. You'll learn that backpropagation is recursive in nature, and this allows us to define the gradients for gradient descent in a systematic way. This recursiveness also allows us to do backpropagation for neural networks that are arbitrarily deep, without much more complexity. In other words, it doesn't matter if you have a neural network with one hidden layer, or a neural network with 100 hidden layers. You can do backpropagation the same way without incurring added complexity. Once we learn about the backpropagation algorithm in mathematical terms, we are going to follow our usual strategy of then implementing that theory in code. First, we'll apply it to the two-dimensional problem we had before, which is the 3 blobs. This is important so you can visualize what problem the neural network is solving. Next, we'll apply it to our e-commerce data. Since we never got a chance to apply softmax to logistic regression in the logistic regression course, we are going to take this opportunity to get more practice by doing that here. This will allow us to compare the accuracy we get when we use logistic regression versus the accuracy we get when we use a neural network. Hey guys, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to enumerate all the symbols and letters we come across in this course. It's important to do this since some of the letters actually conflict with each other, and so you'll need to be aware of the context of what's happening to understand what the symbol is meant to represent. First, when we're talking about training data for a neural network, you've seen that we can refer to the inputs as X and the targets as Y. Generally speaking, these are matrices. X is n by d, which means we have n samples and d input features. Y is sometimes considered to be of size n by 1, where if you're working with matrices, this would be considered a column vector. Note that n by 1 suggests that we're working with a two-dimensional object. Other times, Y can also be considered just a vector of length n, in which case it would be a one-dimensional object. In NumPy, we use this convention. So typically, when we're working in code, Y will be a one-dimensional object of size n, rather than a two-dimensional object of size n by 1. Part of this framework is predictions. So if X represents the inputs and Y represents the targets, then P of Y given X represents the predictions. P of Y given X represents a full probability distribution over all individual values inside the Y matrix given the X matrix. So this is also a matrix of the same size as Y. P of Y equals K given X, on the other hand, represents a probability value. It's the probability that the class is K, given an input vector X. Notice how we typically use lowercase letters when referring to individual samples or vectors, and uppercase letters when we're referring to matrices. P of Y given X is kind of inconvenient to write, especially if you're writing in code. As you know, variable names cannot contain parentheses. So what you'll end up doing is making variable names like these, none of which are really optimal. One old school alternative that you saw in my linear regression course is that we use y with a hat on top to mean prediction. We just call this y hat. But notice how this also cannot be represented as a variable in code. And this is where things get confusing. An alternative way to represent inputs, targets, and predictions is to use x for the inputs, t for the targets, and y for the predictions. This is beneficial in that we no longer need to write out p of y given x anywhere. However, this y conflicts with our other y. Whereas before y meant the targets, now y means the predictions. So you need to be aware of the context in which we are using y in order to tell what it is. If you see y and t at the same time, it should be clear that t is the target and y is the prediction. If you see y being assigned the output of a neural network, it should be clear that y is a prediction. But if you see y and y hat, or y and p of y given x together, then it should be clear that y is a target. So what we just discussed previously is probably the most confusing of all the naming styles we use. The first method was useful because it gave us an idea of what each variable represented, especially the output probabilities. The second method was useful because it allows us to simplify our expressions when we write down equations. I like to expose my students to both so that if you see either of them out in the wild, you'll know what they mean. As you probably already have figured out based on earlier lectures in this course, we have some conventions for the sizes of things. For example, n means the number of samples we collected in our experiment, d represents the number of input features, which is also the size of the input layer in the neural network. M represents the size of the hidden layer, and K represents the size of the output layer. K is the number of output classes and can be anything from 2 or larger. Notice how these are all capital letters. We'll discuss this more later. When we have a one hidden layer neural network, one way to name the weights is as follows. The weight matrix from the input to hidden layer is called W, and the bias term at the hidden layer is called B. You've seen this already in linear regression and logistic regression. In neural networks, we name the weight matrix from the hidden to output layer V, and the bias term at the output layer C. And remember that since W, B, V, and C have to map the vector from the previous layer to the next layer, the size of W must be D by M, the size of B must be M, the size of V must be M by K, and the size of C must be K. You can imagine that if we start adding more hidden layers to our neural network, we are going to run out of letters. So using V and C is not really a feasible option. Instead, we can just number our W's and B's. So from the input layer to the first hidden layer, we can have W1 and B1. From the first hidden layer to the second hidden layer, we can have W2 and B2, and so on. Because W and B are now numbered, you have to index them in a different way than those numbers. For example, you can't make them all subscripts since that would be confusing. One way to do it would be to have the layer number be a subscript, and then put the indices in brackets or parentheses. Another way would be to have the layer number be a superscript, and then have the indices be subscripts. Either of these are fine as long as you don't mix them up. Related to the previous slide, we may or may not put indices in different places if they represent different things. For example, if we're looking at a target t, specifically for the nth sample in the kth class, we can represent this in several ways. In NumPy, we know we'll be storing this as a matrix, so we might write t of nk with square brackets. We might also write t of nk with round brackets. We might also write t of nk with two subscripts. But remember that n and k are kind of different things. K represents which node in the neural network's output layer we are looking at, but n represents which sample from our dataset we are looking at. So we might make one a subscript and the other a superscript. Related to the previous issue is what letters we use to index things. As you know from math and programming, I and j are common indices when we want to do a loop or a sum. We've done this in previous examples. We used I to index the input layer, so I goes from 1 to D. We used j to index the hidden layer, so j goes from 1 to M. and we use k to index the output layer, so k goes from 1 to k. So I, j, and k are all common indices you've probably seen before in a computer programming course you've taken in the past, so there's nothing new to see here. The problem with I, j, and k is again what happens when we run out of letters. What if we have more than one hidden layer, and we need to pick an index outside of these 3 common letters? In that case, it's common to choose letters that are not being used for anything else. For example, like Q, R, and S. Notice the convention here. We use capital letters to mean the total or upper limit, and we use the corresponding lowercase letter to mean the index. Next, we have the learning rate, which as you know we use for gradient descent. Typically, we use Greek letters for the learning rate, like eta or alpha. It should be clear from the context what we are trying to do, since gradient descent always takes the same form. Finally, we have the cost function or the objective function. This is also sometimes called the error function. Typical letters we use are E or J. Usually when we talk about cost or error, we're talking about something we want to minimize. But as you know, the cost functions we've been using have a probabilistic interpretation. What we are equivalently trying to do when we minimize the cost is minimize the negative log likelihood. This is of course equivalent to maximizing the log likelihood. So if you're minimizing the negative log likelihood, then you're doing gradient descent. But if you're maximizing the log likelihood, then you're doing gradient ascent. Typically, we use the capital letter L to mean likelihood, and the lowercase letter l to mean the log likelihood, if they are both being presented together. But sometimes, if we are talking about the log likelihood, or even negative log likelihood by itself, we might just use capital L. This is because a lowercase l can be hard to see. It can be easily confused for an eye. So hopefully this lecture helped answer some questions you may have had about our choices of notation and conventions in mathematics. If you're ever confused about what a letter means, or it seems contrary to what you think the letter means, look at the context it's being presented in. Where the letter is placed, relative to other letters, should give you a sense of what it's being used for.
Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to talk about what it means to train a neural network and introduce some of the basic ideas we're going to develop in the next few lectures. First, let's remind ourselves of the general outline of this course. The previous section of this course taught you how to make a prediction using a neural network. So, given some input, how do you find the neural network's output? Of course, we discovered that those predictions didn't make any sense because the weights of the neural network were just random. In this lecture, we are going to answer the question, how do we find what these weights should actually be? For those of you who are familiar with scikit-learn, here's another perspective. You know that a supervised machine learning model in scikit-learn has 2 primary functions, fit xy and predict x. Fit is for training the model, and predict is for making new predictions using the trained model. So in some sense, what we've done in this course is backwards because we discuss prediction before we discuss training. But in real life, you would have to train the neural network before making any meaningful predictions. Of course, practically speaking, it's obvious why we would want to do this, because training is difficult, whereas making predictions is relatively easy. But not only that, you'll see that training actually requires us to know how to make predictions in the first place. So basically what we're saying is, the previous section of this course talked about what would go inside the predict function, and this section is all about what goes inside the fit function. And as we discussed previously, this involves finding the right weights for the neural network. At this point, I want to make something very clear, which is a common misconception among students who are new to deep learning. While backpropagation is the name we give to neural network training, it is not a special algorithm. In fact, it's very basic, and it doesn't require any new concepts other than what you already know from linear regression and logistic regression. Let me repeat that. When you learn about backpropagation, you're not learning about some new special algorithm. We are just doing the exact same thing that we did to train linear regression and logistic regression. So what is this method that we use to train linear regression and logistic regression? Let's recap the steps. And by the way, if you're new to machine learning, then you want to be very familiar with these steps, since these are the steps that you will follow in pretty much every machine learning model you learn about. So step number 1 is to define a loss function, also known as a cost function or an objective function. As discussed earlier, like any good businessman, your job is to minimize your cost. So step number 2 is to actually minimize the cost. You can do this by finding out which weights, let's just call them W for now, lead to the lowest cost. The question now is, how do we minimize L with respect to the weights W? As usual, we turn to our old friend calculus. Whenever you want to minimize or maximize a function, you take its derivative or its gradient with respect to W and set it equal to 0. Then you solve for W. This makes sense because, as you can see, at a minimum or a maximum, the slope is 0. Of course, in most cases, it's not possible to solve for W algebraically, so we have to use a method called gradient descent. Basically, this involves finding the gradient of L with respect to W, and then taking small steps in that direction over and over again until the loss L converges to its minimum value. We call eta the learning rate, and it defines the step size for each iteration of gradient descent. Now, if you're not convinced that this procedure works, you can check out my gradient descent tutorial to try it out for yourself. But ideally, you already know how this works for linear regression and logistic regression, so it should not be a problem conceptually. One common point of confusion among students is the difference between a gradient descent and gradient ascent. Sometimes it's more convenient to use one or the other, but it's important to realize that they are exactly the same and yield the same answer. For example, if I have some loss L that I want to minimize, then it's possible for me to define some objective J that I want to maximize, which is just the negative of L. To maximize J, I can do gradient ascent rather than gradient descent, but both of these will give me the exact same answer. To prove to yourself that this works, consider the function x squared, which has a minimum. Now suppose I flip it around so I have negative x squared. You'll notice that the minimum of x squared and the maximum of negative x squared are at the same location, x equals 0. But not only that, whether you do gradient ascent or gradient descent, the update equations are exactly the same. Therefore, while they have different names and are conceptually different, mathematically you're using the exact same equation, just with the negative sign in a different place. As a last note for this lecture, I want to address another common mistake, which is to assume that this method only applies to feed-forward neural networks. Again, this is not the case because, as I mentioned earlier, this same algorithm applies to all deep learning models and even some non-deep learning models as well. So we always take the gradient and then take small steps in the direction of the gradient. It doesn't matter how advanced you get in deep learning, whether that's convolutional neural networks, recurrent neural networks, or any other fancy new neural network that's been invented recently. We always use this method. It's just gradient descent. It happens to have a fancy name, which is backpropagation, but realize that it's just the name that's fancy, not any of the technical details.
Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, I'm going to explain to you how to brace yourself for learning backpropagation. Let me explain why this is necessary. For a lot of people, they probably took calculus a long time ago, or worse, they've never taken calculus at all, in which case you probably need to take a few steps back before approaching this section. and so maybe your calculus skills are not as sharp as they used to be. But that's something you can take care of over time. A lot of people confuse the important aspects for the unimportant aspects of backpropagation. In particular, the important aspect, the thing that you should focus on, is actually very easy, and you've done it before. The unimportant aspect is the calculus and the derivation. Obviously, that will improve your understanding, but if you forget why we're doing what we're doing in the first place, that's worse than simply not getting it. I like to say, make sure that you can see the forest for the trees. If you're getting lost on some calculus step, and you think that because of that, you don't understand backpropagation, then you're looking at the trees. The objective of this lecture is to show you the forest. Okay, so what is the important thing that you have to keep in mind for backpropagation? Well, it's that it's actually nothing new. If you've done gradient descent with logistic regression or linear regression, the steps are exactly the same. That may be surprising, but it's true. Let me explain what these steps are. Number one, we're going to set up a cost function. In particular, this is going to be a cost function that's appropriate for multi-class predictions, which is what we're looking at in this class. Let's call that J. Number two, our goal is to do gradient descent on this cost function with respect to each weight of the neural network. Of course, in order to do that, we need to be able to calculate the gradient. This is going to take us down a hill, and eventually we're going to settle at some minimum. And that's really it. That's all there is to training. We just do this in a loop until the cost, J, converges. The thing that most people have trouble with is calculating the gradient itself. But keep in mind that this is just pure calculus. All it is purely mechanical calculation. Follow the rules of calculus, and you end up with some complicated result. So remember, this is not magic, and it's not even an algorithm per se. It's just calculus. We're just trying to find the derivative of something. That's like saying, here's a function x squared, let's take the derivative with respect to x. It's no different from that, except that instead of x squared, we have a much more complicated function. Now, what a lot of other resources do is instead of deriving backpropagation, they simply tell you the answer. They say, this is the equation for the error, then you multiply the error by this term, then you add up these terms, and so on. In my opinion, this is very bad, because when it's presented this way, it appears that backpropagation is some magical algorithm that was invented out of thin air. A lot of beginners are easily impressed by this, but I warn you that this is not the right way to think about this problem. If I wanted to tell you the answer, I would just say, here you go, this is the answer. It's just these equations that you see right here. There's no sense in building up the answer if you don't know where it came from in the first place. When you do that, it just seems like a series of arbitrary steps. I discussed this more in the lecture called The Wrong Way to Learn Backpropagation, in case you want to check that out. Now, let's say you're getting lost in the derivation of the gradient, either because your calculus skills are lacking or simply non-existent. Does that mean you can't proceed? Well, no. In fact, I can tell you the answer right now. You can see the gradient for W, and you can see the gradient for V right on this page. Now, what can you do with this? Well, as always, once we have the equation, the next step is to put that equation into code. As you can see, these gradients involve only two operations. Number one, multiplication. Number two, addition. And I'm sure that if you are taking this course, you know how to multiply and you know how to add, and you know how to do these things in Python. So is there anything stopping you from implementing gradient descent in code? I would think not. So it's important to remember what the steps are here. Number one, we define the cost. Number two, we take the gradient of the cost with respect to the weights, and we come up with some expression. Number three, we take the result of number two, and implement it in code, meaning that we do gradient descent in a loop. Now, the idea in this lecture is that even if you can't do number 2, you can still do number 3. That means maybe you don't understand how number 2 is being done, but you still understand why number 2 is being done. That's good enough temporarily. In the future, you can always come back after you've improved your calculus knowledge. That's totally fine. But don't just give up just because you got stuck on step number 2. That is not fine. Just because you don't understand the mechanics of number 2, that should not stop you from doing number 3. And so the lesson is, even if you don't understand the derivation of backpropagation, it does not mean that you can't skip to the result and do the exercise of translating the equations into code, because the equations only require multiplication and addition, which you obviously know how to do. It's nice to be able to do the derivation, because then you'll understand where the equations for backpropagation came from, but it's not necessary in order to complete the implementation. The steps are the same as always, as they have been since we learned about linear regression and logistic regression. We set up a cost, call that j. We find the gradient of j with respect to the parameters of the model. We then do gradient descent in a loop using the gradient we found. That's the big picture. Don't forget that. Also, make sure you're not learning backpropagation the wrong way, which is doing some random steps for absolutely no reason at all, other than the instructor told you that that's the way it's done. The logic behind that approach is flawed, and I don't recommend it. So hopefully now you understand the big picture, and you remember not to get lost in all the calculus, since that's not really the focus here.
Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to discuss the cost that we want to minimize in our neural network. Let's start by recalling the simplest cost function possible, the squared error, which you should all recognize from linear regression. It is clear from this expression that the more different the prediction is compared to the target, the larger our error will be. Thus, it makes sense to want to minimize this error in order to train our model. By the way, now you also understand why we had to learn how our model makes predictions first. It's because in order to find the error, which is the discrepancy between the target and the prediction, we of course must first have the prediction. As you recall, minimizing the squared error is equivalent to maximizing the log likelihood where the error of our model is Gaussian distributed. Why is that? Let's consider what happens if each target t of n is a random variable which is Gaussian distributed with the mean y of n. The variance of the Gaussian is arbitrary, and it doesn't matter, as you'll soon see, so we'll just say it's sigma squared. Then, given this information, we can set up the likelihood function as follows. It's the product of each individual Gaussian PDF, where t of n is the random variable, y of n is the mean, and sigma squared is the variance. It's important to remember that this is a little more advanced than a typical maximum likelihood estimation problem, because y is not meant to be optimized itself, it's just the model prediction. What we actually want to maximize with respect to is the model weights. So we can think of y of n as a function of some set of weights w. And this w is actually what we want to find. In other words, w is the argmax of L. By the way, when you see the letter L, you might think of loss, but in this case, we actually mean likelihood, which is something we want to maximize rather than minimize. So just keep in mind that the letter L is somewhat ambiguous depending on the context, since both of these words, which kind of mean opposite things, start with the letter L. Now remember that whenever we're solving maximum likelihood problems, it's more convenient to maximize the log likelihood rather than the likelihood directly. So let's take the log of L and see what we get. The first step is to apply the log to each term individually. Since the log and the exponential are the inverse function of each other, they cancel each other out. What we're left with is essentially a function that looks like this, where c means constant. Now, what's interesting about this is that constants don't actually matter. They might yield a different value for the actual likelihood itself, but the likelihood value is irrelevant, since what we care about are the weights w. We just want to minimize L, no matter what the scale is. In other words, it doesn't matter what these constants are, the value of w that minimizes the function will be the same. In other words, we've shown that maximizing the likelihood is equivalent to minimizing the squared error. Let's now discuss a slightly more complicated scenario, which is binary classification. As you recall, for binary classification, we use the binary cross-entropy error function, which is as follows. It's the negative of the sum over n, t of n times log of y of n, plus 1 minus t of n times log of 1 minus y of n. The question now is, what's the log likelihood equivalent of the binary cross-entropy? Well, it turns out that this corresponds to a Bernoulli distributed random variable. In this case, t of n is again the random variable, which is Bernoulli distributed, and y of n is the mean of the Bernoulli distribution. As before, if you want to prove that this is true, you can just write down the likelihood. I think it's almost immediately obvious that when you take the log of this and negate it, you get back the cross-entropy error function which we just saw. And so what we realize is, in both cases, for both regression and binary classification, our cost function or our loss function is actually the negative log likelihood. And by the way, keep in mind I'm just using the letter L for everything here, so don't equate them to each other across different slides. Finally, we have the scenario for this course, which is multi-class classification. With the Bernoulli random variable, where you only had two choices, the sort of real-life interpretation is a coin toss. A coin toss can only give you heads or tails. When you have multiple possibilities, the random variable comes from a categorical distribution instead. The real-life interpretation is a die roll. So when you roll a die, the result must be a number between 1 and 6 inclusive. If you want, you can do a simple example of solving the maximum likelihood problem for an actual, possibly biased die. In this scenario, you would have a series of die rolls, for example, 116, 325, 43. Importantly, it's convenient to represent these with an indicator matrix, which we'll call T of nk. T of nk would be set to 1 if we rolled k on the nth roll. Otherwise, it would be 0. You might also want to think of this as a one-hot encoded matrix. Since for each of the n rows, only one value can be a 1, and the rest must be 0. By the way, as a side note, please remember that when we discuss math, our indices usually start counting from 1, but when we discuss programming, our indices usually start counting from 0. So that's just something to keep in mind and be aware of. Now, because this is a die, we don't have any model predictions, so there are no y's. Instead, we just have the probability of rolling each of the k values. Let's call them w1, w2, up to w6. Then our likelihood is written as follows. It's the product over all n and the product over all k of w sub k to the power of t of nk. By the way, it's good to remember that the likelihood is just the product of PMFs or PDFs for each of the n data points. So if you're not familiar with the PMF of the categorical distribution, please check out Wikipedia to remind yourself. From here, it's easy to see how we would apply this to a neural network. Our output probabilities, y of nk, tell us our prediction for each of the targets, t of nk. So if y of nk is large, then that means t of nk is more likely to be 1. In other words, we can say T of nk follows the categorical distribution given the probabilities y of nk. So this is the same as our die roll example, except we've replaced the number 6 with a more generic big K, and the probability for each category is y of nk rather than just a fixed wk. As usual, our loss is the negative log likelihood, and so we can say that the categorical cross-entropy loss function is nothing but the negative log likelihood given that your distribution of the targets is categorical. As mentioned previously, however, maximizing the log likelihood is exactly the same as minimizing the negative log likelihood. And so I find it useful to just get rid of the negative sign completely, since we'll just end up carrying it over on each line of our derivation, which gets tedious and is basically redundant. As a final note, let's try to build some intuition to make sure the loss function does what we actually want it to do. Remember, if y of nk is very wrong, we want our loss to be large. But if y of nk is very close to the target, meaning it's very right, then we want it to be small. Let's assume we're working with only one sample, so there's no index for n. Then our loss is just the negative sum over k, t of k times log of y of k. Now suppose we are exactly right. Then for the t of k, where t of k is 1, we also have y of k is 1. Log of 1 is 0, so the total loss would be 0, which makes sense. Therefore, if we are perfectly right, then our minimum loss is 0. Let's say now that we only give 50% probability to the correct target. Then we have 1 times log of 0.5 negated, which is 0.693. Now let's say we only give 25% probability to the correct target. Then we have 1 times log of 0.25 negated, which is 1.386. Finally, let's say we are completely wrong. We give 0% probability to the correct target. Then we have 1 times log of 0 negated, which is infinity. In other words, this is very similar to the squared error, where the worst value is infinity and the best value is 0. Therefore, it seems that this loss function works as expected. Let's recap what we've done so far and remember what our plan is. As you recall, we have 2 steps. Step number 1 is to define our loss. We just did that in this lecture. Step number 2 is to minimize the loss with respect to our neural network weights. This is going to involve gradient descent or gradient ascent, and therefore, the next few lectures will involve finding out what these gradients are.